This video is on the objective conduct and interpret a test for homogeneity with the chi-square distribution. Alright, so this is the third kind of test that we're going to do involving the chi-square distribution, a test for homogeneity. And in this kind of a test, you're going to determine whether two distributions are the same or not, right? Or are they relatively close to being the same or not the same distribution. All right. So looking at this first problem here, really again, this is one of those where it's probably just going to be one problem with a bunch of steps, and if you perform all this correctly the first time around, I think you just have to do the one problem to complete the objective. So if you want to see more stuff about this, right, click on More Instruction, look at their videos, their notes, their examples, and hopefully those help you out. I'm actually going to show you some of that here, some of the instruction, just again so I don't have to write it down. Take a while to write. Alright, so here we're conducting a chi-square homogeneity test. And what you're going to notice is that we're basically this is basically the same as the chi-square test for independence. All the same steps. The only difference will be the hypotheses. What are we testing? Alright, so they start off talking here. The goodness of fit test, right, which you've seen, can be used to decide whether a population fits a given population. But it will not suffice to decide whether two populations follow the same unknown distribution. A different test, called the test for homogeneity, can be used to draw a conclusion about whether two populations have the same distribution. To calculate the test statistic for a test for homogeneity, follow the same procedure as with the test of independence. Okay. The only difference, right, however, is the null and alternative hypotheses differ from the test for independence, right? So that's the only thing that's really going to be any different, is what are the hypotheses that are being tested. And a note, and this is the same note that came up in the test for independence, is that the expected values for all the factors must be greater than 5 in order for this test to be valid or be conclusive. All right. So the steps of completing a chi-square homogeneity test, right? Basically the same steps that you follow for any hypothesis test when you're doing the critical value method. So one is, what's the, now in this case for the homogeneity test, are these two distributions the same or not? The null hypothesis will be assuming that they are the same. The distributions of the two populations are the same. The alternative hypothesis will be the opposite of this, right? That the distributions of the two populations are not the same. You have a significance level alpha. You're going to compute a test statistic, right? The chi-squared sub 0 using the expected frequencies. Same way you calculated it for the test for independence, right? The same exact calculation. Determine the degrees of freedom and find the critical value to reject the null hypothesis or not. Then, after you make that decision about the null hypothesis, state your conclusion. Does it seem that the populations are the same or are not the same? All right. Now, the degrees of freedom is the same. Everything's the same. Really, the only thing that's really any different are your hypotheses, the statements being tested here. See, the test statistic is the same. The sum of all these, observed values minus expected values squared divided by the expected values. You add them all up for every cell in a contingency table, where I here represents the number of rows, J represents the number of columns. The degrees of freedom for your chi-square distribution is going to be the number of rows minus 1 times the number of columns minus 1. Again, same as for the independence tests. The homogeneity test is always right-tailed, just like the independence test. Right, so, and then they go through an example here, and I'll let you read these examples in the more instruction on your own. So let's just go through a problem here. Alright, so the question. Do people in different political parties use similar modes of transportation? So researchers ask a group of people about how they get to work. They also group the people by their political party. They want to determine if the distribution of transportation is the same for Democrats, as it is for Republicans. So is the distribution of transportation modes used for Democrats the same as the distribution used by Republicans? The data are recorded in the contingency table below, and a chi-square homogeneity test at the 1% significance level is performed. Alright, so remember, independence tests would have been, is the mode of transportation independent of the political party? This test, however, is determining, does this row, right, the distribution of Democrats, the transportation distribution for Democrats, is that row fitting the same distribution as the second row with the Republicans? Right? Do the Democrats and Republicans have the same distribution? So a little different, the statement there, what we're testing. And we're doing this at the 1% significance level. Alright, so I'm going to write out this table again. Now again, I'm going to put the totals separate. Remember the main table, the actual data, are these 2 rows for the Democrats and the 3 columns for the cars, public transit, and walking. Right, so again, here's the table that was given to us without the totals right now. Again, this is just telling me that of the people, of these politicians surveyed, 25 Democrats take a car to work, 17 of them were Democrats and took public transit to work, 19 of them were Democrats and walked to work, and then 20 Republicans took a car, 6 Republicans took public transit, 20 Republicans walked. Alright, and then you have your totals on the outside. Alright, so down this row here, I'm going to put the totals of the columns. And I'm doing this in a different color because this technically isn't really part of the table. Alright, this is the main table with the observed values from this sample. So the total number of people that took a car in this sample were 45. Alright, the total number of people that took public transportation was 23. And the total number of people who walked is 39. And then down this last column here, I'm putting the totals of these rows. So of these people that were surveyed, 61 of them, right? That's 42 plus 19 is 61. 61 of them were Democrats, and 46 were Republicans, right? 20 plus 6 plus 20. And then in the lower right hand of the table, you're seeing the grand total, basically the sample size, right? How many people were surveyed here? And that's 107. Either you do 61 plus 46 or 45 plus 23 plus 39. And this is usually called like lowercase n for this is the sample size. Alright. Now the question here is the transportation distribution for Democrats the same as the transportation distribution for not all Republicans and all Democrats? This is just a sample, and then based on this sample, what can we say about the population of all Democrats and all Republicans? are their transportation distributions, can we reasonably say that they're the same or not? So those are our hypotheses, right? So the null hypothesis here in this test for homogeneity is that the transportation distribution for Democrats is the same as for Republicans. And this is for the population of Democrats, and the population of Republicans is the same as for Republicans. Okay? And then the alternative hypothesis is that they are not the same. I'll just write that. The transportation distribution for all Democrats is not the same as the transportation distribution for all Republicans. So I'll just simply write they are not the same distribution. Okay, and then like with any other hypothesis test, right, what we're going to be assuming is the null hypothesis, and then deciding if we like that later or not. Are we going to reject this statement or not? So we're going to start off assuming that the distributions are the same, and then go from there. All right, and then after this, usually we identify a significance level. They already told us, right, the value of alpha here, we're doing this test at a 1% significance level. So the value of alpha is 0.01. Right. All right, but then that's the start of this, right? What are the hypotheses? So back here, right, make sure you pay attention to the labeling, right? The distributions of the two populations are the same for the null hypothesis, and for the alternative HA, the distribution of the two populations are not the same. And that's the way it's going to be for all of these homogeneity tests. Alright, and then I'm sure they're going to have us find the test statistic, which, and I'll show you a couple ways to do that. And one with the calculator, and then I'll do the long way first, and then a shorter way with just the calculator. Alright, because now, the next part is compute the test statistic, rounded to 1 decimal place. And they're asking us to do it in a specific fashion. Use expected frequencies that are also rounded to 1 decimal place. Alright, so hopefully you recall from the assignment about the tests for independence, the expected frequencies were found thusly. Expected frequencies for each of the 6 cells in black here, right? The ones that aren't totals, the actual observed counts. Well, if I want, what's the expected frequency for the ith row, jth column? All right, I comma j here. Well, hopefully you recall this formula. That was the row total for the ith row, ri, multiplied by the column total for the jth column, cj, divided by the total sample size, n. Alright, so for instance, if I wanted what's the expected frequency for the number of Democrats who take a car to work, the first row, first column entry, I take the, so I'm here, I'm in the first row, first column, so I take the row total for that row, 61, multiplied by the column total for that column, 45, and then divide this product by the total sample size, 107. And they're asking us to round all these expected frequencies to 1 decimal place, right? So I'll pull a calculator up. Let me enter this as 61 times 45 divided by 107. All right, so this first one, rounded to 1 decimal place is approximately 25.65 would go to 0.7. All right. And I'll put that in like a light green underneath so you have your observed value, and then beneath this I'm writing the expected value for that first row, first column cell, 25.7. All right, and then for the first row, second column, first row, second column, I take the first row total, so now I'm here in this cell. First row total, 61 again, times the second column total was 23, divided by the sample size, 107. Right. So the nice thing is I've already entered most of that, so I can just hit second entry and just change the 45 to a 23. And there we go, approximately 13.1. Right, if I round to 1 decimal place like they're asking me to. So it's approximately 13.1. Alright, and let me just do this real quickly for the others. Right, so for this first row, third column, I'll just do second entry again, because I'd be taking 61, I'd take 61 times 39 over 107. So I'm just going to change the 23 to a 39. And I'll write this under here, approximately 22.2 for the expected value of the Democrats who walk to work. All right, and now in the second row, for this cell, the Republicans who drive a car, multiply 46 by 45, the row total times the column total, and then divided by 107, again divided by the sample size. So 46 times 45 divided by 107, and rounding to 1 decimal place, that's approximately 19.3. Okay. Then here you have 46 times 23, so I'm just going to change the 45 to a 23. So approximately 9.9 if I round that to 1 decimal place. And then for the second row, third column, Republicans who walk, 46 times 39 divided by 107. So again, I just need to change the 23 to a 39. And about 17.8, sorry, 16.8. 16.8 rounded to 1 decimal place. Okay, so now for the test statistic. All right, remember the test statistic is this chi-squared value, right? Chi-squared sub 0, and it's just, the sum of all those. You're going to take every observed value minus its corresponding expected value, square that, and then divide by the expected value. And you do it for every single cell. So I'm going to have 6 terms here. So I'm going to have, 25 minus 25.7 squared divided by 25.7 plus all the way, you do it again 6 times, 1 for each cell, all the way down to pardon me, this last cell, the second row, third column, where I would take 20 minus 16.8, square that, and divide by 16.8. Now I've got a quick way to do that for you with lists. All right, so on my calculator, I'm going to enter these observed values in a list, and I'm going to enter their corresponding expected values in another list, but make sure that things line up properly. So I'm going to hit Stat, go to Edit, and down list L1, I'm going to enter these observed counts, right? 25, 17, 19, 26, and 20 again. All right, those are all the observed counts. And then down list L2, I'm going to enter the corresponding expected counts, right? All the green numbers to one decimal place. Now again, make sure 25 has to line up with 25.7. Right, every observed value has to line up with its corresponding expected value. So then I got 13.1 to go with the 17, 22.2 to go with the 19, 19.3, 9.9, and finally 16.8. And you've seen me do this before, right? I have the observed counts, the expected counts. Then I move over to list L3 and move the cursor up to L3, hit enter, and I'm going to enter a little formula where in parentheses I'm going to take the observed counts, which were from list L1, minus the expected counts, which were from list L2, close parentheses and square that, divided by the expected counts, which were from list L2. Alright, so then these 6 values are what I'd get here in this sum, and then I'm going to add those up, right? I'm going to take the sum of the values in list L3. So I get out of this, go to the list area above stat, over to math, hit number 5 for sum, and I'm going to add up the values in list L3. And there we go. Right, our test statistic, rounded to one decimal place would be approximately 3.8. Chi-squared equals 3.8. Alright, so that's what I'll enter here. Right, that's how they asked me to calculate this thing. Right, using the expected frequencies rounded to one decimal place, and then have the test statistic also rounded to one decimal place. And look at the answer explanation here. It's exactly what I was showing you. I mean, they wrote the whole thing out. I didn't, but got 3.8. Now, if you'd like to do this in a faster way, right, again, you may recall me doing this in a previous assignment. Another way to do this with your calculator, a quicker way, is to make a matrix of your observed values, right? So again, we have 2 rows, 3 columns of these observed values. So I go to that matrix menu above the x to the minus 1 button. I go over to edit, hit enter on whatever matrix you want. I'll just do matrix A here. And then this is rows by columns, right? I said there were 2 rows, 3 columns. And then I just enter, the first row, first column there, 25 for the Democrats who take cars. Then Democrats who take public transportation, 17, then 19. All right, then the second row of my observed values, 26 and 6. I'm sorry, 26 and 20. All right, so now I have all my observed values entered in a 2x3 matrix. Get out of here. And then if you want the test statistic right away, just go to the chi-squared test, just like for independence. I hit the stat button. I go over to tests and down to C where it says chi-squared test. Chi-squared test. I hit enter on this. And it asks you for a couple matrices. Now if you put if your matrix with the observed values wasn't matrix A, you're going to have to go back to that matrix menu and then under names pick the matrix you did have the observed values in. But it was already matrix A, so I didn't need to do that. And just make sure that the expected matrix is a totally different letter. Alright, this is matrix B, which I didn't enter anything into, but it will automatically calculate that for us. Alright, then I hit calculate. And look, chi-squared equals 3.81, which if I rounded this to one decimal place, it would round to what I had here, 3.8. Amazing. Now again, if you've been watching my other videos in previous assignments related to this chi-squared test statistic, you may have noticed that sometimes they round to the same thing and sometimes they don't, because the calculator is more accurate. This is not, when I was doing this calculation earlier, I rounded all these expected values to the nearest tenth, and then also rounded the final answer, right? And in the process, if you round, the more and more you round throughout a calculation, the less accurate your final answer is going to be. So just be careful that, sometimes this might be a bit off. So if you do this, if you enter the matrix with your observed values and then run the chi-squared test, and you enter this test statistic here around a 1 decimal place, if it comes back and says you're wrong, then you're going to have to go back in and round all the expected values to 1 decimal place and do what I did earlier. But it'll be really close. I mean, if it's not 3.8, if it came back 3.7, it'll be off by like it'll be off by like 1 at the last decimal place. All right, it even gives you like a p-value and the number of degrees of freedom for your chi-squared thing. But again, we're only focusing here on the test statistic. All right, additionally, you know how I calculated all those expected values earlier? Well, if I did this, if you ran this chi-squared test, go back to that matrix menu, you see how now there's a matrix B filled in 2 by 3? And look at this. If I enter matrix B on my main screen, look at down the first column here, 25.65, that's 25.7, which is what I wrote here. This second row, first column, 19.3 is what I got earlier. And if I scroll right a little bit, all right, it jumped quite a bit. Now you got 13.1 for the first row, second column, then 9.88 or 9.9, first row, second row, second column. And then you see in over here, one more time, 22.2, first row, third column, 16.8, second row, third column. So you just scroll left and right, and you can see all these expected values. Or you could also go over to the edit area down to matrix B, and you can see them here as well. This is probably easier actually. So you see all the 25.7, 19.3, 13.1, 9.9, 22.2, and 16.7, 16.8. Exactly the values I got earlier without all the typing. Right? All I had to do to find this was type in that matrix of observed values and run that chi-squared test. And then this matrix of expected values will pop up automatically. Right? It's a beautiful thing. Alright, so again, hopefully watching me do this on the calculator, writing stuff out, looking at the more instruction if you need to, looking at the answer explanations when they show up, and hopefully remembering all the stuff you did for the test for independence. It's the same calculations. Hopefully all that stuff will help you when you go about doing this on your own. And thank you very much for watching.